Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about series and convergence and how they relate to our last video on sequences. Okay, so we're going to be tying the two together now. We'll be reviewing a little bit about series real quick, and then we'll try to tie the two together. All right, so let's get started. Let's talk about some terms that you need to remember. A series, if you recall, is the sum of the terms of a sequence. Okay, so here's your notation, sigma, all right? And then there's a counter. In this case, it's the variable I, and it could be any variable you want, but in this case, it's I, starting at 1 and then going up until n of a sub I. So for example, what this means is the counter would start on 1. I would plug in 1 for I. So a sub 1 would be my first term of the series. Plus, the counter would then click to 2. So then I'd plug in 2, a sub 2. Plus, then the counter clicks to 3, a sub 3. The counter clicks to 4, a sub 4. I plug in 4. And then eventually, I reach the end of the line. The end of the line is wherever n is. So that would be a sub n. Okay? And again, you plug these numbers in. So I'd plug in I equals 1, I equals 2, I equals 3, I equals 4. But the important thing to understand here is that now we're adding the terms. Okay? In a sequence, right, we're listing them with commas. But in a series, we're going to add those numbers. Okay, so the series for this sequence would be 1 plus 3 plus 5 plus 7. We're adding them, not listing them with commas in the middle. All right. Now, what we're actually most interested in this chapter are what are called infinite series and their sums. So, for example, if I were to take this sequence and expand it a little bit, and I were to write 1 plus 3 plus 5 plus 7 plus 9, that's a series, but I were to continue to do that forever, it's an infinite series. Okay? The question is, what is the sum of that series if I were to add all of these terms up? All right, that's what we want to try to determine. Okay? So, in some cases, an infinite series will approach a finite value. In other cases, it will not. But I think the first thing that's most important is I need to convince you that you can add an infinite number of numbers and still get a value that's finite. Okay? All right, so let me do that. I'm going to do that here on this next slide, which is completely blank. All right, so here's how this works. Basically, I'm going to do this game here. And in this game, I'm going to try to shade in this entire slide. But I got to do it with certain rules. So for example, the first shade that I shade, I can only shade in half of the slide. All right, so this is close to half, I guess. So I'm going to shade in half of the slide the first round. Okay, there it is. So that's half of the slide. Now, for the next round, I'm going to shade in a quarter of the remaining portion of the slide. So here's a quarter of it. I'm going to shade that in. Remember, I'm trying to shade in the entire slide. All right, in round 3, I'm going to shade in 1/8 of the remaining part that's unshaded. Here's 1/8 of it. Shade it in. Remember, we're trying to shade in the entire slide. Okay, the next round is going to be 1/16 of the entire slide. So that small piece there, the pieces are getting smaller, right? All right. Now, obviously, you can take a guess what the next piece would be, hopefully. That would be 1/32 of this slide. Okay. And then I would keep doing that. All right. Keep that pattern going. Now, what I'm doing is I'm literally adding all of these terms together, right? 1/2 of the slide, 1/4 of it, 1/8, 1/16. I shaded 1/32, then 1/64 it would be, okay? But what I want you to understand is if I were to add this and do this forever, eventually Okay, at some point in time, I would reach the point where I had this one slide that would be shaded in. So it looks certainly, if we go to the next slide here real quick, this is the series that we developed on the previous slide. Take 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, plus we keep going. So it certainly looks like if I were to ask you what is the sum of this series, it certainly looks like the sum of the series would be 1, right? If I added all of these together forever, eventually I'd get one shaded in slide. Okay? But the question is, how would we calculate that? We can't add these numbers forever. There's no way that we could do that. And, we'd just be here forever adding numbers, and that doesn't make a lot of sense. But mathematicians want to know, how would we calculate that? So what we would do is we're going to find what are called the partial sums of this series. Okay? A partial sum is the sum of the first n terms of a series. So here's what I mean by that. It's actually a pretty simple concept. If I wanted to find s sub 1, the first partial sum, it would be, of the series up there, it would be 1/2. Just the first term in the series. If I want s sub 2, the second partial sum, I would have to take 1/2 and add 1/4. Okay, take the first two, right? Terms of the series and add them together. Now I could do that pretty easily, right? Find a common denominator, you get 3/4. If I wanted s sub 3, I would take the first 3 terms of the series and add them together. 1/2, 1/4, and 1/8. 8 would be my common denominator, and I'd end up with 7/8 when I was done. Okay, s sub 4 would be 1/2 plus 1/4 plus 1/8 plus 1/16. And you folks get the idea. If I were to add all these together, that would be 16 on the bottom, 15/16. Okay, so now here's what I'm going to do. All of these are partial sums. The first partial sum, the second partial sum, the third partial sum, the fourth partial sum. What I can do is I can make a list of partial sums. Here are my partial sums in a list. 1/2, 3/4, 7/8, 15/16. And I would keep going with that list, right? But wait a minute. Now we're saying I'm making a list. We talked about making lists that have patterns. They're sequences. This is a sequence of partial sums. But here's the thing about sequences. We know if a sequence converges or diverges. We know how to figure that out. And we also know that if it converges to a finite value, and that value is the sum of the sequence. Right? So we know how to do that. If we could take the limit as n goes to infinity of this sequence, then we can determine whether or not this series will converge or diverge. So what we need, though, is we need an nth term, right, for this list of partial sums. So n equals 1, n equals 2, here's n equals 3, here's n equals 4, and we can find it. The bottom is pretty easy to find, 2, 4, 8, 16. We're going up by powers of 2. So that would be 2 to the n power, right? If n is 1, you get 2, n is 2, you get 4 on the bottom, n is 3, you get 8, n is 4, you get 16. On the top, if you look, the number on the top in the numerator is 1 less than the denominator every time. So if I take 2 to the n and subtract 1 up on the top, well, yeah, 2 to the first is 2, 2 minus 1 is 1. 2 to the second is 4, 4 minus 1 is 3. 2 to the third is 8, 8 minus 1 is 7. Okay? This is an nth term that represents this sequence of partial sums. So now if I were to find the limit of it as n approaches infinity, well, if I plug in infinity, I get infinity over infinity. That's indeterminate. So you can either use L'Hopital's rule or divide by the dominant power. The dominant power would be 2 to the n, right? So that would be the limit as n goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. Sorry, folks, I'm trying to squeeze this in here. That would be a 1. The limit as n goes to infinity here. 1 over something really big is really small, goes to 0. 2 to the n over 2 to the n is 1. 1 over 1 is 1. So the sequence of partial sums converges to 1. But 1 is also the sum of the series. So obviously that can't be a coincidence. So let's try to generalize it. If the sequence of partial sums has a limit that's equal to L, like in our last slide, it was equal to 1, then the infinite series also converges to L. It also converges to 1, which we figured out 2 slides ago when we were shading in that slide. L represents the sum of the series. So the sum from I equals 1 to n of a sub I is equal to the limit of that sum, which is the limit as n goes to infinity of s sub n. This is the sequence of partial sums. Okay, the sequence of partial sums, the nth term of the sequence of partial sums, it's equal to L. If the sequence of partial sums diverges, then the infinite series diverges. It doesn't approach a finite value. Okay, you can add those terms forever and you'll simply get something like infinity. You'll just keep adding over and over and over again and you never get anything finite. All right, so let's put this to the test here and show you how it works real quick. So if the sum of the first n terms of a series is given by this sequence of partial sums, 3n squared over 4n squared minus 5, we can find the sum of the series by taking the limit as n approaches infinity of the sequence of partial sums. So again, if I throw in infinity here, I get infinity over infinity. That's indeterminate. You could use L'Hopital's rule. You could divide by the dominant power. Dominant power would be n squared. If I take all the terms and divide by n squared, that would be 3n squared over n squared over 4n squared over n squared minus 5 over n squared. So that would be 3 up top. Underneath would be 4 minus the limit as n goes to infinity of 5 over something really big is really small, goes to 0, 3/4. So the sum of the series, whatever that series was, is 3/4. Okay, so that's how this all works. Now, the idea behind this is, well, that's how you actually find the sum of the series. But in math, we always want to do things in an easier way. So that's what's coming. Okay, as always, thanks for clicking.